So section 6.3 is more on counting methods, and we're looking at some more advanced counting methods, in particular permutations and combinations. So to get us started with this, let's pretend we have a table, and on this table is a phone, the switch, an old He-Man figure from the 80s, for some reason a spool of thread, and a disembodied foot with a brace on it. And what I want to do is count the number of ways that I can choose objects from this table and take all of them off. I want to count the number of ways I can choose all 5 of these objects off the table one at a time. So, starting out, I have 5 different things I can choose from. So let's just suppose that I take the iPhone off first. So once I've made that choice, before I take the iPhone off, I have 5 different objects I can choose from. And after I make that choice, I have 4 objects left to choose from. I have the disembodied foot, the spool of thread for some reason, He-Man, and the switch. Right now, I make another choice, and I have 4 choices, and now I'm going to take off the spool of thread. Once I've done that, I have disembodied foot, He-Man, switch, so there are 3 objects to choose from. So multiply that by 3. Now I'm going to take the foot off, and that's going to leave me He-Man and the switch. So now I have 2 objects left to choose from. So I'll multiply by 2. So let's take He-Man off. No, let's not. Let's take the switch off. This doesn't matter for the math. I just want to be left with He-Man. Right, and now I have 1 more thing left to choose from. So I'll multiply this by 1, and then we'll take He-Man off. Right now, the reason that I'm multiplying 5 times 4 times 3 times 2 times 1, that comes from that fundamental counting rule, that multiplication principle from section 1. I'm counting the number of ways I can take objects off the table one at a time, and so I'm multiplying, and the choices go down each time. And so, as you all know, 5 times 4 times 3 times 2 times 1 is equal to 5 factorial. Right? That's the notation we use for 5 times 4 times 3 times 2 times 1. So that's the number of ways I can choose all 5. If I have 5 things on the table, this is the number of ways that I could choose all of them one at a time. There are 5 factorial ways. Now, before I go on to the first definition of this section, I do want to point something out. So let's now suppose we're starting off with an empty table. I'm going to erase all these calculations we did before. And I want to figure out how many ways I can choose 0 objects off that table. Now, one way to think of permutations as far as a definition goes is it's the number of ways to choose objects off a table. So n factorial, which is equal to n times n minus 1 times n minus 2 down to 3 times 2 times 1. One way to think of this as the number of ways to choose n objects. So the question arises, what is 0 factorial going to be? Well, think of it like this. I have nothing on this table. How many ways can I pick up 0 objects? And the answer to that question is 1. There is 1 way that I can pick up 0 objects. And that 1 way is I don't pick up anything. So 0 factorial is equal to 1. And if that bugs you and you don't like that reasoning, we can talk about it in class or something. And if it does bug you, and it does bug some people, just think of this as a definition. We define 0 factorial to be equal to 1. All right? Okay, now let's go on to the definition of what a permutation is. And it's going to tie back into this table example. So a permutation of a set of distinct objects is an ordered arrangement of these objects. Okay, so before I do this example, I want to focus in on this term ordered, because it's super important. Okay, it's an ordered arrangement as opposed to something something called a combination we're going to see a little later where it's not ordered. But I want you to write this down somewhere, and I want you to remember it. So when you're doing a permutation, two things. No repetition, that is, you cannot choose an object more than once. So there's no repetition, and the order you choose them in matters. So think about that example that I did with the table. What I was doing was an ordered arrangement of the 5 objects on that table, because choosing out the spool of thread first is different from choosing the the He-Man action figure first. So those would be 2 different arrangements. So what we did, we actually did a permutation of objects in that previous example, and I don't remember what the order was, what order I chose them in. But if I had, chose the switch first, that would have been a different arrangement, so a different permutation than the one that I did in that example. So we can also do this with sets. So if I want to look at all of the permutations of the set ABC, so what I want to do is figure out the different ways I can arrange the letters A, B, C, where the order matters. So I could, first of all, I could just have A, B, C, that's one permutation. Or I could have A, C, B, that's different because the B and the C, the orders are swapped. Or I could have B, A, C, I could have B, C, A, I could have C, A, B, or I could have C, B, A. And that's all of them. This is all of the different ways to arrange that. Now, I know that's all of them because, I was very systematic in the order that I wrote them down in. However, there are 3 objects there. And if you think about this as the number of ways you can choose them, I have 3 choices for whichever one I pick first. Once that one is gone, I have 2 choices for the second one I pick, and then 1 choice for the last one I pick. So that is 3 factorial, which is equal to 6. It's exactly the same thing that I did with the table full of random objects. It's just 3 factorial in this case, 5 factorial in this case. So the permutations of n objects would be n factorial. Now, you don't have to choose everything in a set when you're doing a permutation. Think about if I had that table and I wanted to count the number of ways that I could just choose 2 of them. That's what this next little bit is going to be about. So n is a positive integer, and r is an integer that's in between 1 and n. When that's the case, there are p parentheses n comma r, and this is permutations of n objects r at a time. And this is called r permutations of a set with n distinct elements, or permutations of n objects r at a time. And the way you calculate that is n times n minus 1 times n minus 2 down to n minus r plus 1. Now, I know this can look a little bit confusing, but in practice, it's really easy. So let me show you an example. So what I have here is a set with 4 elements. So n is equal to 4, and I'm choosing 2 of them, so r is equal to 2. So what I'm doing is I'm counting permutations of 4 objects taken 2 at a time. Well, if I follow the definition up there, it's going to be 4, and then look what happens. I just keep going down. N times n minus 1 times n minus 2, so I would have 4 times 3. And when do I stop? Well, I stop when I get down to n minus r plus 1. N is 4, minus r would be 2, plus 1 would be 3, so I stop. So it's just 4 times 3. So that is equal to 12. So there are 12 different ways to choose 2 objects from that original set of 4 objects. So you stop counting down on multiplication when you get one more than r. Okay. Let me show you another formula that I believe it's in the book, but sometimes people find this one just a little bit easier. Another formula for permutations is this. Permutations of n objects r at a time is equal to n minus r factorial. Whoops, nope, that's wrong. Let me erase that. It is n factorial divided by n minus r factorial. Okay, so if I want to use this formula, I would have permutations of 4 objects taken 2 at a time. I have 4 factorial over 4 minus 2 factorial. And I'm going to show you a little trick you can use if you don't happen to have your calculator. And by the way, I will show you how to use your calculator to calculate permutations with big numbers. There's a permutation function on your calculator that you can always use. But watch this. 4 factorial is equal to 4 times 3 times 2 times 1. 4 minus 2 is 2 factorial. So that's 2 times 1. So look, 2 times 1 cancels with 2 times 1 down here, which just leaves a 4 times a 3. So you can always do this little trick. You'll always be able to use the bottom factorial to cancel out a lot, or at least some, of the numbers that are on top. So whenever you're doing this calculation, you'll always be able to do that. And again, I'll show you in class how to use your calculator to do this. Okay, now we're moving on to combinations. And a combination of elements of a set is an unordered selection of elements from that set. So before we do these examples, just like with permutations, I want you to remember this. When you're doing combinations, you're going to be choosing without repetition, so no repetition is allowed. But now, order does not matter. So when you're doing combinations, the order doesn't matter. So always remember that. For permutations, order matters. For combinations, the order doesn't matter. Which, it's always funny to me when I think about this. On the very first slide, I had a really fancy combination lock. And when you're doing a combination lock, the order you put the numbers in does matter. So they really should be called permutation locks, not combination locks, but, you know, whatever. Okay, so let's look at this example right here. If we want to think combinations of this set A, B, C, it says here aka subsets. So combinations are just going to be subsets because in a set, the order doesn't matter. Now, if I'm taking, again, the context right now is going to be this example right here. So what I'm writing the rest of this slide is going to be for this example. If I'm taking combinations of all 3 objects, so combinations of 3, there's only one. It's just A, B, C. Because, you know, there's only one way to choose all 3 of them if the order doesn't matter. If I write down BAC, it's the same thing because the order doesn't matter. This is the same thing as choosing BAC because in combinations, order doesn't matter. Have I said order doesn't matter enough? Yeah, order doesn't matter for combinations. Now, if I'm taking combinations of 2 of them at a time, what would that look like? Well, I could choose AB, I could choose AC, or I could choose BC. And that's it, because anything else that I write down, if I write down, BA, it's the same as this one. If I write down CA, same as this one. CB, same as this one. So there are 3 ways to choose combinations of 2 of them. And then if I want to see how I can make combinations of 1 of them, well, combinations of 1 one of the elements from that set, I just choose A, B, or C. That's it. So there's also 3 ways to do that. Okay? So, just like with permutations, I don't have to choose all of them at a time. Okay? As a matter of fact, the most interesting and most real-world problems involve having larger numbers of things to choose from and only choosing a few of them at a time. And when that happens, we need the following formula. So the combination of a set with n elements, where n is a non-negative integer and r is a number between 0 and n inclusive. Okay, this is combinations of n objects chosen r at a time. So there's 2 ways this is usually said. Sometimes this is said as, what I just read to you. Combinations of n objects r at a time. But more frequently, this is just read as n choose r. N choose r. And this is what you'll see if you look at, or you may see this if you look at other books or other websites. You may see it just read as n choose r. And actually, while I'm thinking about it, let me go ahead and show you some other notation in case you do look at some outside resources. Combinations of n objects r at a time is sometimes written as n choose r. And this is actually sometimes written like this, in parentheses, n choose r. So you may see that notation sometimes too. And the notation we had for permutations of n objects r at a time, this is sometimes written as, including on your calculators, as np r. So you'll see that there's no parentheses notation for permutations, but you may see these other notations sometimes. I'll do my best in class to stick to these because it's what the book is using, but I want you to be aware of these other ones just in case you come across them in future classes or in, again, looking at outside resources. Okay, let's do some examples. Okay, so we're going to do example 1. So there are, in this problem, there are 12 people trying out for a baseball team, and they can only take 9 players. So 9 of those 12 people are going to be on a team. And the question is, how many different teams can they make? How many different ways can you take 12 people trying out, and choose 9 of them to be on a baseball team? Well, there are 12 people trying, so n is equal to 12, and we're going to be choosing 9 of them. So r is equal to 9. So this is combinations of 12 objects taken 9 at a time. So this is equal to, according to this formula up here, this is equal to 12 factorial divided by 9 factorial times 12 minus 9 factorial. Now, we can play that same little game we had a second ago, where we do the cancellations. So before we do, let's just write this as 12 factorial over 9 factorial times 3 factorial. Now, I can do the cancellations using either the 9 factorial in the bottom or the 3 factorial. You want to always choose the larger number because you'll cancel more stuff out. So this is equal to, again, the denominator has a 9 factorial and a 3 factorial. So think about what 12 factorial is. It's 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But I can also write that as 12 times 11 times 10, and instead of writing out times 9, 8, 7, 6, 5, 4, I can write this as 9 factorial. Because 9 factorial is the 9, 8, 7, 6, 5, 4, 3, 2, 1. And now it's really clear to see I'll be able to cancel out the 9 factorial down here with the 9 factorial up here. And so this is going to be equal to 12 times 11 times 10 over 3 factorial, which is 6. So 6 will cancel with 12 and leave 2. And I just have 2 times 11 times 10, which will be 220. Because 2 times 11 is 22, and times 10 will make it 220. So there are 220 ways to, 220 different baseball teams you can make from the 12 people who are trying out. Okay, and I didn't say this earlier, but I probably should have. The reason this is a combination is because I'm just going to choose 12 players first, or excuse me, 9 players first from the 12. I'm not deciding on positions. I'm just making a team. So the order that I choose these people in doesn't matter. And once I choose a person from the 12 to be on my team, I can't choose that same person again. And so there's no repetition allowed. All right, let's look at the next example. So for this example 2, a test has 30 true-false questions. So I have a test with 30 questions, and 15 of them are going to be true. So how many possible answer keys could there be? Well, I have 30 objects, which in this case are true-false questions, and all I know about them is that exactly 15 of them are true. So 30 test questions, 15 are true. So what I'm doing is I have 30 objects and I'm choosing 15 of them. Okay, and that'll give me how many answer keys there are. So if I just plug this into the formula, I'm doing combinations of 30 objects chosen 15 at a time. So this is 30 factorial over 15 factorial times 30 minus 15 factorial. So this is equal to 30 factorial over 15 factorial times 15 factorial. Now, these numbers are getting so big that they can't comfortably be done by hand. We could, in theory, do this, but it would just be a pain in the butt. So what I'm going to do in the meantime, before I can show you in class, is beneath this video, I'm going to post a link to a web resource that shows you how to do combinations on a TI calculator. So look under the video, or look in the description of the video, and you'll see that link. All right, let's move on to some more examples. Think about the baseball thing we did, where we had 12 people trying out, and we chose 9 people to be on the team. What if instead of choosing 9 people to be on the team, we were really cruel and just started out by pointing at the 3 people who were just really bad and said, you people aren't going to get to play. Okay, so we're going to choose 3 people not to play. So that would be a situation where we're calculating combinations of 12 objects, and we're choosing 3. We're choosing 3 people who aren't going to be on the team. So this would be 12 factorial over 3 factorial times 12 minus 9 factorial. Whoops. Not 9, 3. I was thinking ahead of myself. 12 minus 3 factorial, which is 12 factorial over 3 factorial times 9 factorial. Now this is the exact same expression we had just a second ago. So this is going to be 12 times 10 times, not 12 times 10, 12 times 11 times 10 times 9 factorial over 3 factorial times 9 factorial. 9s are going to cancel out. 3 factorial is 6, so that'll cancel with 12 and leave 2. And so this is going to give us 220 again, which is the same answer we had before. And that's what this box up here is saying. If n and r are non-negative integers with r less than or equal to n, then combinations of n objects chosen r at a time is always the same as combinations of n objects chosen n minus r at a time. So that's just a nice thing to keep in mind sometimes, that n choose r is the same thing as n choose n minus r. Because choosing 9 people to be on your team out of the 12 is the same thing as choosing 3 people not to be on your team out of the 12. And you'll always get the same number whenever you're doing that. Okay, this example is asking, how many different ways can you deal a pair with 2 cards total? Now, this example and the next one I do like this one, I want you to really pay attention. So if you have anything else going on, any music playing, anything on TV or something like that, stop it, and then stop all that other stuff so you can really focus on this, because this will take some concentration, okay? So first of all, remember that, well, what's a pair? A pair means 2 cards, same rank. So the rank, remember, is the value of the card, like ace through king. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. That's the rank. So a pair means you have 2 cards that are the same rank. So if I want to count the number of ways to get a pair, the first thing I have to do is think about how many ranks there are. So out of the 13 ranks that all the cards have, every card is going to have ace, 2, 3 through king. So there are 13 different ranks. The first thing I have to do is I have to choose from those 13 ranks one of them. Okay? So this right here, this is counting ranks. This is counting how many different ways you can choose one of the 13 ranks. But then that's not all that I'm concerned about. So when a given rank is chosen, so for example, suppose I choose 5. Well, there are 4 different 5s in the deck. There's the 5 of hearts, the 5 of clubs, the 5 of diamonds, and the 5 of spades. So once a rank is chosen, out of the 4 different suits, I'm going to choose 2 of the suits. Okay? I'm going to choose 2 of those suits to make my pair. So this is counting the ways to pick 2 cards, same rank. So that's how you have to do this problem. Now, of course, you don't always have to write this explanation stuff that I did in red. You just have to write the counting problem, the combination stuff down. But you have to count the number of ways to choose a rank, and then from the 4 cards that are of that rank, you have to count the number of ways to pick 2 of them. And so this will work out to be combinations of 13 objects one at a time is going to be 13 factorial over 1 factorial times 13 minus 1 factorial multiplied by 4 factorial over 2 factorial times 4 minus 2 factorial. And this works out to be 13 factorial. 1 factorial is just 1, so 13 minus 1 factorial is 12 factorial, multiplied by 4 factorial. 2 factorial is 2 times 1, which is just 2, and then 4 minus 2 factorial would just be 2. So this works out to be 13 multiplied by 4 times 3 times 2 factorial over 2 times 2. So these cancel. 2 cancels with 4 and leaves 2. So we are left with 13 multiplied by 6, which is, what, 78? So that means there are 78 ways that if you are dealt 2 cards, you'll get 2 cards that have the same rank, 78 ways. Now, I want to do the same problem, but see what happens if we do it with 5 cards total. which would be more typical of an actual poker hand. So how many ways can you deal a pair with 5 cards total? Well, we start out the same. You want to count the number of ways to choose the pair. So you're going to be dealt 5 cards. And 2 of them here are going to have the same rank. And these other 3 are going to have ranks that are different from these 2, but in particular are different from each other, because otherwise we wouldn't have a pair. We'd have a 3 of a kind or something like that. So how can we count this? Well, we start out by dealing with the cards that are the same rank. It's combinations of 13 things chosen one at a time. Because of the 13 ranks, I'm going to choose one of them for my pair. And then I'm going to multiply that by combinations of 4 objects chosen 2 at a time. Because for the chosen rank, that gives me the pair, I take 2 of those cards. So this deals with this part. Now I have to deal with this part, count how many ways I can choose 3 other cards. So there are 12 ranks left in the deck that haven't been used to make my pair. So out of those 12 ranks, I'm going to choose 3. So this is 12, choose 3. Okay? Now why? Why is that the case? Because again, I'm using one of the ranks to form my pair. These 2 cards have the same rank, whether it's 2s, 3s, whatever. So one of the ranks is being used up to make the pair. That leaves 12 other ranks. And all of these need to be different, because otherwise it wouldn't be a pair. The hand wouldn't have a pair anymore. If this had the same rank as these 2, then I would no longer have a pair of cards. I would have 3 of a kind. So all of these ranks need to be different. So out of the 12 ranks that haven't been used for this one, I'm going to choose 3. 1 rank here, 1 rank here, 1 rank here. Now, for each one of those, for each rank, so for the rank chosen for this card, say it's 7s. There are 4 7s in the deck. Of those 4, I'm going to choose 1 for this card. So I'm also going to multiply this by combinations of 4, choose 1. But that same thing is going to happen for this card. Whichever rank is chosen for this one, out of the 4 of them, I'm going to choose 1 of those cards. Same thing with this one. So I'm going to be doing 4, choose 1, 3 different times. So all I'm going to do is raise that to the 3rd power. Okay? And then I'm not going to write out the final answer. This would be a nice one for you to practice doing it on your calculator. And again, look for the link in the description to see how to do that. And so this is the last example from this section. Try to start on this homework before we get to class, because I'm sure that there are going to be questions. And if you've already been working on it, then you're at least developing some intuition, and you're seeing where you get stuck. And we will, spend a couple of days working on this until we can get you kind of unstuck. Now, like I said in class, counting things does have some applications in and of itself. Sometimes it's useful just to count things. And we'll actually see some of this later in the semester when we do graphs and trees. But the main motivation right now is to do probability. Okay, and that's what we're going to be starting on in Chapter 7. All right, I'll see you in class.